Welcome to Module 3, Functions. Functions are at the very core of calculus, so it is extremely important to practice various ways to represent functions, function notation in particular that gives people a lot of trouble, and things that describe functions, such as domain and range, how to combine and compose them, and of course, inverse functions. Generally, we think of 4 different ways to represent a function: analytic or formulaic, so using a formula; graphical, given a graph of a function; numeric, with a table of values; or verbal, with simply a description. In this module, we will cover all the different ways to represent function and make sure that you develop fluency going from one representation to another. Let's start from the very beginning and talk about what is a function. A function is a rule that assigns to each element of a set exactly one element of another set. The way to picture it, often you are suggested to think about an input into the function. So the function is a box that takes an input and produces some kind of output. So notice here that a function is a rule that assigns to each element exactly one element of another set, which means that this black function box here is what we call deterministic. So if you do give it an input, it knows exactly what output corresponds to it. There is no choices that the function has to make. Some examples, some real-life examples, include, for example, car to license plate. To each car, there is exactly one license plate that corresponds to it. Or student and student IDs. So if you tell me a name of a student at U of V, I will be able to tell you 3 registrar function, exactly one student ID. Another way to picture it a little more abstractly is there are a bunch of inputs that are available for a function, and when we apply a function, let's call it f here, the function produces a bunch of outputs. The set of all possible inputs, so this blob, is called a domain. And the set of all possible outputs is called a range. So let's just make it clear. Domain, set of all possible inputs. And a range is a set of all possible outputs. So in our example here, for example, for U of V, the inputs are all the students at the university, so the domain are all the students, whereas the outputs are all the student IDs, so the outputs are all possible or are all assigned 9-digit student numbers at U of V. Let's take a look at something a little more precise and not as abstract. So some functions with very particular functionality. By the way, think of the word function. How does it function is exactly where it gets its name. So here, every input number gets doubled, which means that I can still write this in this pictorial form where I have input. Whatever I give to this function, it doubles my input and produces an output. We can, of course, agree that whatever I put into this doubling function here, it will produce exactly one output. So it's not like it has to make a choice somewhere in the doubling process. Now, the input can be anything here. Any number can get doubled, right? And so I can, of course, go through examples and say, what if the input is 4, then the output is 8? What if the input is 3? Then the output is 6, and so on. But if I want to describe it in a little more generality, I can say that the input can be any number x, and then the output will be twice that number. This notation is called a variable, and that, of course, again, comes just from the English word variable. It means it varies. So it's not one fixed entity. It's not just 4 or just 6. It can be different numbers. And so the function notation in this case is going to be, I'm going to have to give this function a name. It's a doubling function, so let me call it capital D. What goes after it is the name of the input, equals, and what goes on the right-hand side is the output. So let's label all of this. This D represents function name. You can pick a name for your function, much like you would pick a name for your child. This X inside represents input, and this 2X here represents the function output. Okay? This is what we call a function notation. Let's try this on another example. Every input number gets flipped. So here, let's start with some numbers. So for example, if I give this function a 7, it will output 1/7. If I give it a -2, it will output -1/2. If I give it 1/3, it flips that, and the output will be 3. So, as we've talked about here, the domain are all the possible inputs if I continue. So these guys represent the domain, and the range will be all the possible outputs if, once again, I actually continue on and produce as many outputs as are possible for all the input values. Of course, right away, we notice that if my input is 0, 0 can't get flipped because we cannot divide by 0, which means that domain is immediately going to exclude the value of 0. Thinking about all the other numbers, we quickly come to the conclusion that any other number but 0 will be able to get flipped, which means that the domain is all the numbers except for 0. If we were to come up with a function notation for this function, again, I'm going to use x as my variable. So the function is the flip function. So let me call it f. I give it an input x, and whatever that input x is, it's going to get flipped. So it's going to be 1/x. And for just a little exercise here, try to write down the expressions for f of x plus 2. So what would happen if x plus 2 gets flipped, as well as f of x plus 2. So notice the differences here. In this first example, the entire input is x plus 2, so this whole thing will get flipped, whereas here the input is x, so the function is only applied to this x, and then the plus 2 is added on afterwards. Write out what these guys are going to be. This is good practice in the preview for more practice with function notation we're going to do shortly. There are a number of ways to represent functions. This is what we would call an analytic or formulaic representation when a function is given to us directly by a formula. Here's an example of a function given to us via a verbal description, and we're asked to write down an corresponding analytic or formulaic version of it. So let's take a look at this example. Every tablet of Tylenol contains 325 milligrams of acetaminophen. I hope I'm pronouncing correctly. Approximately 67% of the drug is removed from the body every 4 hours. Ksenia, that's me, has taken an initial dose of X milligrams 4 hours ago and had just swallowed 2 more regular tablets of Tylenol. Okay, so 4 hours ago, I took X milligrams of it, and we know that 67% of the drug is removed from the body at that time interval during the 4 hours. The question is asking, having just ingested 2 more regular tablets of Tylenol, what is the total amount of the drug in my system? So let me call that function. It's the amount of acetaminophen in my system. So let me call that function A. And it's asking, given the initial dose that I don't actually know, so it's a variable, it could have changed, it is unknown, what is the current amount of drug in my system? So I know I have just swallowed 2 regular tablets of Tylenol, each one of which contains 325 milligrams of the drug, plus I still have whatever is left of the drug from 4 hours ago. I know that 67% is going to be removed, which means that 33% of my initial dose is still in my body. So here I'm going to have to add 33% of the initial dose. Okay? The next part asks, what is the implied domain of the function? Implied meaning in context, so keeping in mind what the actual situation that we're using this variable is in. Looking at the function itself, we can see that x appears only up here, and in fact, if we were to graph this, this is just going to be a line. And so no matter what x is, I will be able to plug it in here. But remember that x stands for the amount of acetaminophen in the blood, which means that it can of course not be negative. It has to be 0 or more. So the implied domain here is going to be x greater or equal than 0. Mathematically, x can be anything. In context, it has to be 0 or above. The next part is asking to describe the amount of the drug in my system 4 hours from now. So we know that every 4 hours, 67% of whatever drug is present is going to get removed. This amount is what is currently in my blood, which means that 4 hours from now, let's call that function b, I'm going to have 33% of this amount left in my body. Okay, so 33% of 2 times 325 plus 33x. So this is the current amount. And in 4 hours, I'm going to have 33% of the current amount left. Excellent. This is how one turns a verbal description of what a function is into an analytic or function notation type of the function representation. Let's practice more with the function notation in the analytic description of the functions. So here I have two functions, f of x and g of x, and I'm asked to evaluate a number of different things given the analytic representation of the function. So one thing that's important, let's just take a look at f of x first. One thing that's important to notice is that this x is simply a placeholder. So it represents whatever it is that you need to plug in into a function. So let me maybe highlight this. Whatever this x is, it's the exact same thing as appears throughout. So whenever I'm asked to compute with a particular value, I simply replace x with the value that I am given. So f of 3 then will be 3 squared minus 2 times 3 plus 3. So notice that if I simply sort of highlight this 3, the function form, the function structure will be exactly the same. And that's the whole point, is that it should not change whatsoever. I am using this x as just a way to represent what's going to happen to any input that I choose to plug into my function. Okay, so let's take a look at the next one. Here, I am asked to compute g of 3. So I'm going to be replacing x with the 3 every time I see it inside of the function g. So 3 plus 3. And I'm going to leave this unsimplified just so once again, the function structure remains very clear. F of 10 means once again, I'm going to replace all x's in f with 10. So 10 squared minus 2 times 10 plus 3. And g of minus 10 means I'm going to now replace x with negative 10 every time I see x in the function g. So it's going to be square root of minus 10 plus 3. And here, of course, I can see that I have an issue because this is going to be a negative number. I cannot take square roots of negative numbers, so this is actually undefined. Undefined. Now, usually, students don't struggle with plugging in actual numbers into the function. The struggle shows up when we start replacing variables with variables. But please remember that the same exact logic holds. If you have to compute f of t, that means that this t has to replace x in your function every time x appears. So f of t will simply be t squared minus 2t plus 3. Okay, and similar for the next one. F of t plus 2 means that my new input is t plus 2. This is my entire new input. So this whole thing has to replace x at every occurrence of x in my function notation. So this will then be t plus 2 squared minus 2 times t plus 2 plus 3. Okay, so again, if you sort of just highlight this throughout, you will notice that it's the exact same structure as f had in the first place. It's input squared minus 2 times the input plus 3. If my input is this, it's still input squared minus 2 times the input plus 3. Okay, so be very careful to treat this whole thing as an input and not leave the 2 outside of the function somehow. The other functions that we're going to work quite a bit with in calculus are so-called piecewise functions. They are given in pieces, hence the name, and you're going to have always a function followed by the condition on when that piece applies. So when we're asked here to evaluate h of 3, the first thing we have to do is to decide where does 3 fall into, the top piece or the bottom piece here. So is 3 less than or equal than 0, or is 3 greater than 0? Well, 3 is greater than 0, which means that I'm going to be plugging it into the second portion of the function here. Okay, so I'm going to have 3 cubed plus 5. So notice that I'm not going to be plugging it into both because a function produces exactly one output. Okay, so I cannot have two different outputs for the same value of x. I have to pick exactly one that will satisfy the condition that the input actually belongs to. Following the same logic, h of minus 5, I have to decide, does minus 5 belong to where it's less than or equal than 0 or greater than 0? So is minus 5 in the first condition or in the second condition? Now, of course, minus 5 is less than or equal than 0, so I'm going to plug it into my first function, which will then give me minus 5 squared minus 3. Okay, and notice here that it's minus 5 all squared because minus 5 is the entire input, so this will actually turn out to be positive. And lastly, h of 0. So again, I have to decide, is 0 less than or equal to 0 or is 0 bigger than 0? And I notice that 0 is included in the top function here, so I'm going to be using that top one to plug 0 in. So it's going to be 0 squared minus 3. Okay, so keep in mind that even though the function is given in two separate pieces, only one of them applies at a time. Now, let's discuss the domain and range of a function for specific functions and not in general. Once again, let's just recall that the domain is a set of all allowable x values, so all the values that can be plugged into the equation that result in a real number. So you cannot, for example, like we did here, have square roots of negative numbers. And the range is the set of all the possible outcomes or outputs. So here we have three different functions, and we're going to determine the domains of them. The range is sometimes very tricky to determine without the graph, so we're just going to let it be. But the domain is something that we're always concerned about because this will tell us exactly what values of x we can and cannot use as inputs into the function. So this first function here, I have x divided by something that also involves x. The moment you have a division sign, you're going to start being careful because, of course, we cannot divide by 0. And this is something that we're going to have to take into account because there is an x on the bottom here in the denominator, which means that there are values of x that will produce 0 on the bottom. So the domain cannot include values of x that will make denominator 0. Moving 3 over, we can see that x cannot be equal to negative 3. Okay, so my domain, there's nothing else here that will result in a non-real number if we plug it in. So the domain will be all real numbers except for x equals to negative 3. For the next function here, we have a square root. Now with square roots, as we've seen before, we cannot have a negative value under the square root. Cannot take square root or any even power root at this point. It cannot take square root of a negative number. So that means that whatever goes under the square root has to be positive. Now we can take a square root of 0. Square root of 0 is just 0. So that means that x minus 3, which is the thing under the square root here, has to be greater or equal to 0. It is allowed to be 0 because once again square root of 0 is 0. Solving for x, we have that x has to be greater or equal than 3. Great. This last one actually has both of aforementioned issues. It has a denominator and it has a square root, so that we're going to have to make sure that none of those things are actually causing us any trouble. So first of all, we cannot divide by 0, which means that x squared plus 4 cannot equal to 0. Now, there's a couple of ways to think about this. If I move the 4 over, I'm going to get that x squared cannot equal to negative 4. Or I can just look at the equation as is and notice that no matter what x I plug in here, it's going to get squared, which means it's going to become positive, and then I'm going to add a 4 to it. Already positive number plus 4 more will never be 0. So this has no solutions and therefore produces no exclusions for the domain values. The second part is the fact that I have a square root and I have to make sure that whatever is under the square root is positive. So I have to have that 5x plus 3 is greater than or equal to 0. Again, I can take square roots of 0 and this square root is on the top. So having a 0 on the top here will not be a problem. Solving this inequality will give me that x has to be greater or equal than minus 3/5. Okay, so as long as it's greater or equal than this negative 3/5, this square root, we will be able to compute, and this whole fraction will not be something that is divided by 0. So the domain here are all values of x that are greater or equal than minus 3/5. One more thing we need to discuss in general are inverse functions, and we will see inverse functions when it comes to things like exponentials and logarithms, as well as trigonometric functions. Inverse functions, again, the name here is pretty intuitive. It means exactly what it sounds like. So thinking of one of our first abstract examples, let's say student gets assigned a student ID. And this, of course, is a function, right? To every student, there is exactly one student ID that gets assigned, but I can also go backwards in this case. So if you give me a student, I can tell you what student ID that person has at U of E, but if you give me a student ID, I can also look up and see what student corresponds to that particular student ID. So let's say if going forward was something that we called function f, then going backwards is something that we call f inverse, okay? And that is a notation for it. In terms of a more pictorial representation, if I have some input x and I apply a function f to it, I'm going to have an output f of x. If I apply the inverse function, it's going to take me back to the original. We write f to the power of minus 1. And this represents the inverse function, not the reciprocal function. So the negative 1 here is written in the power, which, let's say if it was just x to minus 1, it would represent 1 over x. But this is just a shorthand that we use for inverse functions. It means the inverse function, not the reciprocal. Some inverse functions are really easy to think of. Inverse functions simply undo what the original function does, right? So for example, I can come up with a really quick example here. If my original function is, let's say, add 3, then its inverse will have to undo what the original one did. So if the original added a 3, the inverse will subtract a 3, okay? There are algebraic methods to actually come up with to solve for the inverse function, and I hope you remember some of them from precalculus. But let's just go through all the 4 different representations of a function to think about how we can describe inverse functions. So first of all, verbally, inverse simply undoes what the original function did. So once again, if the original added a 3, then the inverse will subtract a 3. Symbolically, we can think of that as following. If I have my input x and I apply a function f to it, and then I apply the inverse, then I should just get my original input back, because the inverse, f inverse here, undid what the original did. So in a sense, they cancel each other out. And of course, I can apply the exact same process in the reverse order. So if I start by undoing something and then doing it, then I should get my original x back. Analytically, and that is how to find the actual inverse of a function if you're given an analytical expression for the original function, we will reverse roles of x and y. And you probably remember doing that in Precalculus. And then we will solve for y. Graphically, we can draw inspiration from the analytic process. Reversing the roles of x and y means simply reflecting the graph in line y equals x. Okay, so you have a little diagonal line, and whatever your function is, you're gonna have to reflect it in this line to get the inverse. So let's say if this is my original, then the inverse is simply reflecting it in this line, so something that will look like this. Let's next talk about operations on functions, which means that if you have two different functions, what are some of the ways to actually combine them? Let's first take a look at the 4 basic arithmetic operations, and they will actually work the same on functions as they do on numbers. So if you have an input x and you want to apply a function f plus g to it, it's the same as first applying the function f, then applying a function g, and adding the two outputs together. With a difference, it's going to work the same way. Notice my wonderful typos here, except for we're going to be subtracting the functions. If you want to multiply two functions together, it's the same as first applying them and then multiplying together the outputs. And if you want to divide the two functions, you can apply, once again, get the two outputs first and then divide them by each other, provided that the denominator here is not going to be 0. Now, these are just the 4 basic arithmetic operations, and they work the same as arithmetic operations on numbers. So I've broken up this module into several parts for you to be able to practice with. Please, at this point, take a look at WebWork Assignment Module 3A. The other function operation that does not have a corresponding meaning in terms of arithmetical operations is a function composition, which means that we're going to apply functions one at a time in sequence. So let's say I start with some input x and I apply the function f to it. Then the output is going to be f of x. And then I'm going to apply another function to this output. Let's call it g. So I'm going to go through these 2 levels of function application. I start with an input x, apply the function f to it, and then I take this whole thing as an input and I apply function g to it. So on the output here, I'm going to have g of f of x, where this f of x now becomes an input to the function g. Now, of course, I could have done that in different order, right? So I could have first applied the function g to the input x, and I would have gotten g of x as the output. And then if I were to apply function f now, notice that now g will serve as my input into f. So what I'm going to get is f applied to g that's applied to x. There are 2 notations for this. This is just one of them, and the other one will have a little circle in the middle. So f of g of x corresponds to f of g of x, and the other way around, g of f of x, the little circle in between, corresponds to the other order. Notice that generally the order will matter, and so these 2 things will actually be quite different. Also notice that as we're working, and we'll see this in example very shortly, we're going to work inside out. Okay, so this is my original input. I then have to calculate the first function applied to this input, and then I'm going to go all the way out to f. So I start from the inside, move on to the next function, and move on to the next one after that. Let's take a look at an example here. So I'm given the same two functions or similar two functions as I had before, a cubic and a square root function. And first I'm asked to just compute the actual arithmetic operations on them. So by what I have above, arithmetic operations will transfer naturally, whereas function composition is a new operation that we probably want to spend a little bit more time on. So f plus g of 1 is the same as f of 1 plus g of 1. And now this I can compute by simply plugging in 1 into the function f and 1 into the function g. So 1 cubed minus 2 times 1 plus 1. This will be my function f of 1 plus g of 1, which will be square root of 1 plus 2. Okay? The next one here, 2 times f minus 3 times g, all evaluated at 4. So this is the same as 2 times f evaluated at 4 minus 3 times g evaluated at 4. And again, now that I've broken it up into something in terms of f, or something for the function f and something just for the function g, I can plug those in directly. Okay? Let's take a look at the next one. This is f divided by g at 2. So this is the same as f of 2 divided by g of 2, and provided that g of 2 is not 0, which it's not, I should be able to evaluate that. Okay, so plugging 2 into f will give me 2 cubed minus 2 times 2 plus 1. Plug in 2 into g will give me square root of 2 plus 2. Now let's take a look at the function composition here. Okay, so remember what I said earlier, you're going to have to work inside out. So first we're going to have to compute the internal portion, which in this case is g of negative 3. G of negative 3, I'm going to then plug in the negative 3 directly into g, which will give me square root of minus 1, which is undefined. So this entire expression is going to then be undefined. So let me change the question just a little bit so we can actually get a numerical answer. What if I had a plus 3 in here? Then my first step is I have to evaluate g of plus 3. So again, that means plugging in plus 3 into the expression for the function g. So I'm going to get for this square root of 3 plus 2, or square root of 5. And this is now the input that I'm going to plug into the function f. So my next step is I have to compute f of square root of 5. So I now plug square root of 5 into my function f, which will give me square root of 5 cubed minus 2 times square root of 5 plus 1. Okay, so be careful, working inside out, not outside in. If we want to write down a general equation or a general expression for the function f of g of x, that means that I have to take the function g of x, which is, of course, square root of x plus 2, and plug that as the input into function f. So now I have to calculate f of square root of x plus 2, which means that I have to replace every occurrence of x in my function f with square root of x plus 2. So what I'm going to get is x plus 2 square root cubed minus 2 times square root of x plus 2 plus 1. Okay, now in the opposite order, if I have g of f of x, that means that I have to first plug x into the function f, which will then give me g of the function f, which is x cubed minus 2x plus 1. And now I have to plug this entire expression into the function g every time I see x in there, which will give me, so instead of x, I'm going to have this entire function in g. So x cubed minus 2x plus 1 plus 2. So this guy was my f of x. Okay, so very clearly now in this example, this expression is not the same as this expression. So obviously the order of function composition application matters. So be very careful about that. For this last one here, it's just another exercise in function notation application. Again, this is now the input into the function f, which means that this expression will have to replace every occurrence of x in the function. So I'm going to have s plus 7 cubed minus 2 times s plus 7 plus 1. If you'd like to open up the brackets and simplify this is fine. This is something that we're going to have to do when we get to the definition of the derivative later in calculus. One of the other representations of a function is a numerical representation, or when a function is given to you by a table of values. So here I don't have a formula, I just have to work with the function values calculated at specific points. But we can calculate various or evaluate various expressions for the function in the same way as we have before. So here I'm using the circle notation, but this reads as h of k of 5. So let's first rewrite it that way. I find that this nested notation a little bit better because you can really see what the layers are that surround 5 and which order to apply them in. Okay, so first of all, I'm going to calculate k of 5. And so let's see how this table works. The first row gives me values of x, then it's values of h at specific points x, and then values of k. So k of 5 means my x is 5, and I'm looking for the value of the function k, which will be this one right here. So k of 5 is 1, which now means that I have to calculate h of 1. I have to go back to the table. So now my input is 1, and I have to calculate the h function for it. So overall, I have 7. Okay. Next one is k of h of 2. And following the same logic, what am I going to get? Working inside out, I first have to figure out what h of 2 is. So my input is 2. H of 2 turns out to be also 2. So at the next step, I now have to calculate k of 2. So once again, my input is 2, but now I'm looking for k output, which will be 9. So this again highlights the fact that, oh, never mind, they're actually computed different outputs. Okay, next one is h inverse of -3. So please remember that this corresponds to inverse, not reciprocal. What the inverse function does is it's the exact opposite of the original, which means that what I am given on the inside is the output of the original function, and what I'm asked for is what input will produce -3 as the output of h. Okay, so that means that I have to look at function h and where does output of -3 happen. This row corresponds to outputs of the function h, and -3, I can see it right here, corresponds to input of 4, which means my answer here is going to be 4. Okay, so let's go through this once again. Inverse function means that what I have inside is the output of the original function. So I have to look for the output of the function h and find what input that was originally representing. Okay, and then going through all of these is going to be very similar in fashion to the ones before. So let's see, we're going to work inside out. So first I have to compute, oh, there's no g, I think this is supposed to be k of 0. So first I'm looking for input of 0 and the value of k, which will then be 8, which means this is 8. And the next thing I have to do is compute the inverse, h inverse of 8. So once again, this means that this is the output. So I will be looking for what input of h produces the output of 8. So I'm looking at the row of H and I'm looking for output 8. It happens right here, and the input that corresponds to it is 5. Okay, in the same fashion, we will take a look at the next one, H inverse of 0. So that means my output is 0 for H. Where does the output of 0 for H occurs? Right here. The input for that is 3. So this expression is equal to 3. And next step, I am computing K of 3. The input is 3. K of 3 is going to be 5. Okay, and for the last one here, H inverse of 8. Where does 8 occur in this row? Right here. In fact, we've already computed this here. So the H inverse of 8 is 5. And now I have to compute K inverse of 5. So I'm looking at the row that represents outputs for K. I'm looking for the value 5 there. And what input did that correspond to? Corresponded to input of 3. And in fact, what we notice here in the last two examples is exactly the relationship between the function and its inverse. A function computed at a certain input produces an output of 5 here, which means that an output of 5 is produced by the input of 3, and this is how one would write it using the inverse function notation. Following analytic, numerical, and verbal descriptions of a function, there's of course a very important graphical representation of a function. As we've discussed, a function establishes a relationship between an input and an output. You get to choose what the input is, which is why this is called an independent variable. And then whatever is given to the function as the independent variable will produce its own output, which is why the output is what we call the dependent variable. It depends on the input, but both of them vary, therefore they receive the name variable. Graph is not just a picture, it is a representation of this relationship. So what is very important to recognize is that on the graph, every point, let me write this out because this is essential for understanding graphs. Every point on the graph of a function satisfies the function rule, satisfies the function relation or the function rule or whatever you want to call it, satisfies the function relationship. Okay, so for example, if I take the function f of x equals something, let's keep it simple for the first example, 3x minus 1. That means that if I am to sketch a graph of that function, what I'm really sketching are all the points where y coordinate is equal to 3 times the x coordinate minus 1. This is why the table of values works, because what I am sketching is exactly the set of all the points where x and y are in this relationship together. Okay, so here, if you want to just plot a couple of points, we can plug in your chosen values of x, because again, remember, this is my independent variable, so you get to pick what you want x to be. Let's say minus 1 or 0 or 2, and then y is going to be dependent on your choices of x. So if x is -1, I plug it into here. I can compute the corresponding y value, which will be -4. If x is 0, I can plug it into here. I compute the corresponding y value. It's going to be -1. If x is 2, I can compute the corresponding y value. It will be 5. The table of values gives me pairs of points that correspond to the function, to the function's graph. So at x equals -1, I have -4. So this point right here. When x is 0, y is -1 right here. When x is 2, y is 5. Notice that, of course, this is something that you will likely recognize as a linear relationship, and therefore its function is just a line, which means, once I sketch this line, So what is important, let's pretend it's going through all those points, it's actually straight. But what is important to recognize is while I only sketched 3 points, every single point on this line that I choose will have x and y coordinates that satisfy this relationship. Every single point on that line, out of the ones that I chose or out of any of the other ones, and there's infinitely many of them, will satisfy this relationship. Okay, with that in mind, here are some common functions that you should probably have some idea of what their graphs look like. So please take a minute, and on the next page, you have a bunch of graphs that are provided. Sketch what the graphs of these relationships will actually look like. We will, in further modules, talk more about functions like polynomials, reciprocals, and of course, exponential functions. So for a more detailed discussion on the particular functions, look out for future modules. Sometimes the function is only given to us as a graph and not as a relationship together with a graph. So here I have the graph of a function wx, and I'm asked to simply read information about the function from the graph. This is going to go over the exact same things as we've seen before. So things like domain and range, as well as inverse, function compositions, and operations on functions. So you should be comfortable with being able to come up with all of this information, whether the function is given to you as a graph or as an analytic formula. Okay, so with this graph here, the definitions of things don't change. So the domain are still all the possible x values. And notice that my graph only exists along the x-axis between this point and this point, which means between -5 and 3, including the endpoints, because notice that these points are actually on the graph. So my domain is going to be from -5 to 3. Range are all the possible y values, and so in thinking in terms of y, or the height, we can see that the lowest the graph is at -5, and the highest it is at 4, again including the endpoints, because those points are actually included on the graph. So the range is between -5 and 4. Stating the x-intercepts are a very natural graphing concept, because this is talking about when does the graph intersect the x-axis. And of course, we can just read this directly off of the graph. So the x-intercepts are -4, -1, and 1. X-intercepts have very deep algebraic meaning, because these are also what we call roots or zeros of a function. So when we're having to calculate or solve for those, it's exactly the same as solving for the x-intercepts. Y-intercept is, of course, where the graph crosses the vertical axis, y-axis, and there's one only point here, -1. And in general, if we remember that a relationship is a function if it passes the vertical line test, we will notice that for a function, we will only have one y-intercept. And if we have more than one, then the graph does not represent a function, but rather just a more general relation. Evaluating specific function values from the graph, we just have to read off the y-coordinates for the corresponding given x-coordinate. So when x is equal to 1, right here, the y-coordinate of the point on the graph, in this case, is 0. When x is -1, the y-coordinate is once again 0, and this actually corresponds to the fact that -1 and 1 are in fact x-intercepts. So the y-coordinate will be 0. For this next one, w of 0 plus w of 3, we will have to compute them separately. W of 0, so when x is 0, y is -1, and when x is 3, y is 1. So I'm going to have -1 plus 1, which altogether comes out to be 0. For the next one, w of 0, which was -1, divided by w of 3, which was 1, I can simplify to be -1. Function composition, in this case, the same function is applied twice, works the exact same way as we've done it before. So I have to work inside out. I have to first compute w of 2. So when x is 2, the corresponding value of y is 3. And then at the next step, I have to compute w of 3. W of 3, of course, is this point right here, whose y-coordinate is 1. Moving on, w of minus 3. So first I have to compute w of minus 3, which is 4. So then in my next step, I have to compute w of 4. X equals 4 is right here, and there's no function at this point anymore. Notice that the domain only goes up until 3, which means that w of 4 is undefined. Recall that this notation corresponds to inverse function. So that means now I am looking for the input that produces the output of 4. Output of 4 means y equals 4. So I'm looking for the points where y-coordinate is 4, and there is one right there at negative 3. Okay, and the same logic applies to the next question. I am looking for the input that will produce the output of 1. So the y value is equal to 1. Let me note this here. Y has to equal to 1. What does the x value on the graph equal to when y is equal to 1? Well, when y is equal to 1, I have quite a few points that actually match this condition. So which one do I pick? Right? And that is the problem here. If I cannot pick one, if it's not unique, then that inverse is also not well defined. Which brings us to the discussion of the vertical and horizontal line tests. In order for a graph to represent a function, it has to pass a vertical line test, which means that for any vertical line I draw, the graph of my function has to cross it at most once. And that is, of course, because if I have a graph and it crosses the vertical line, let's say twice, then the function won't be able to decide which output to give you, this one or this one. A function is deterministic. It has to have a unique choice. So every vertical line has to be crossed at most once. Okay, so the vertical line test determines whether a graph is that of a function or not. As we've just seen here, what that means for inverse functions is the horizontal line test. So if I am to draw a horizontal line, if the inverse is to exist, it has to cross that horizontal line at most once. Otherwise, I'm in the situation like I was in the last example above, where I am unable to decide which one of these outputs, or rather inputs of the original function, to take. Okay, my choice has to be unique, which means that an inverse will only exist if any horizontal line crosses the function at most once. So the horizontal line test corresponds to the existence of function inverse. This is again consistent with how we've discussed the inverse graphically. Remember that a function, if I give you a graph of a function, you can come up with the graph of its inverse by simply reflecting in line y equals x. Well, if your drawing was a function to begin with, it means that it had to pass a vertical line test. A vertical line becomes a horizontal line when flipped in y equals x. So if what you had originally was not a function, what you will have after a flip is something that does not have an inverse. Okay? So if you are to have both a function and one that has an inverse, it means that the graph of that function has to pass both vertical and horizontal line tests. Now, the next page is reserved for you graphing those common graphs, such as x, x squared, x cubed, square root of x, cube root of x, a couple of reciprocals, as well as the exponentials. Once you do that, please feel free to use table of values so you really get a feel of how to produce points on the graphs. After this, please take a look at WebWork Assignment Module 3B for all kinds of practice when it comes to functions. Function notation as given to you by the formula from the graph or from the table of values. The exercises at the end of this section are also extremely useful to practice fluency between different types of function representations including analytic, including graphical, including verbal, that are all going to appear again in calculus.